Hi everyone, this is Samira, and today we're going to be focusing on the fundamental theorem of calculus. Now, this is a very important topic that frequently pops up on the AP exam for both Calculus AB and BC, so it's very important that every calculus student understands this topic. Let's first start out by looking at an example to better understand this concept. Now, let's start out by drawing a graph. This will be t, this will be y, and here we have the curve f of t between the points a and b. Now, let's define a new function, f of x, which will be the area under the curve of f of t between a and some value of x. And to show that we're finding the area under the curve, we can use the integral sign, a to x, f of t dt. Now, this is where the fundamental theorem of calculus comes into play, and we can actually use it. So say we were asked to find the derivative of this function between a to x, f of t, our final answer would just be f of x, because the integral and the differential would undo each other, and we would just be left with f of t, and since we're dealing with x's, we would just plug in the x instead of the t, and this would be our final answer. And the cool thing about the fundamental theorem of calculus is that it acts as a bridge between the world of differentiation and integration, and it connects the two seemingly different topics, which shows that both of them are inverses of each other and they undo each other. Therefore, the final answer that we got here is said to be true. Now, to show that differentiation and integration are actually connected, say we had to find the derivative of some function x to the power of n. To differentiate this, we would first bring the n to the front, and then we would subtract by 1, which would give us this answer. Now, however, if we had to integrate the same function x of n, we would first have to add a 1 and then divide this whole term by the new exponent, which would give us this final answer. As you can see, in differentiating, we subtract a 1, while when we're integrating something, we add a 1, which shows that there's a connection and that they are inverses of each other. Now, to make this more clear, let's look at an actual real-world calculus problem. Okay, so say we had a function 0 to x of square root of t squared plus 4 dt, and we were asked to differentiate this whole thing, dx. Now, some things to keep in mind is that f of t is the square root of t squared plus 4, and capital F of t is the antiderivative of lowercase f of t. So now we can simplify this problem into 0x f of t dt. Now, after integrating f of t, we will get the derivative of capital F of t from 0 to x, because f of t, capital F of t, is the antiderivative of lowercase f of t. And so now all we'd have to do is plug in the bounds of the integral, which would be f of x minus f of 0. So now if we were to find the derivative of capital F of x, we would get lowercase f of x, and since f of 0 will give us some constant, the derivative of a constant will be 0, so we won't even have to worry about that at all, which would therefore give us a final answer of f of x, and since f of t is equal to t square root of t squared plus 4, we would just plug in x where all the t's are, and we would get this as our final answer over here. Now notice how in this example we had the x as part of the upper bound of the integral, and our final answer was a positive answer. Now, had the x been in the lower bound of the integral, the steps would be the same. You would do the same thing here, except the f of x over here and then the f of 0 here would be switched, which would result, here, let me write that, minus f of x. The derivative of this would still be 0, so that would cancel, and we would have a negative answer instead of a positive, which is something that is good to keep in mind in case the x is switched. Okay, now let's take a look at a little bit trickier problem, which asks us to find the derivative of the integral from 5 to x squared, square root of t cubed minus 4 dt. Now, as before, some things to keep in mind is that f of t, the function, is equal to square root of t3 minus 4, and that f of t is the capital F of t is the antiderivative of lowercase f of t. Okay, so now with that in mind, we can somewhat simplify this into integral 5 to x squared f of t dt, which will we can then integrate, and that will then leave us with capital F of t from 5 to x squared, because capital F of t is the antiderivative of lowercase f of t. And now we will just plug in the bounds of the integral into our function f of t, which will give us fx squared minus f of 5. Now the only thing that's different about this problem is that instead of having an x, we have x squared. So when we're finding the derivative of this term over here, we can use the chain rule, which will give us 2x, which is the derivative of x squared, and f of x squared. And since f of 5 will give us some constant, the derivative of that will just be 0, so we can just cross it out. It's irrelevant. And now all that's left to do is find what f of x squared is. And since we know that f of t is equal to square root of t3 minus 4, we're just going to plug in the x squared wherever we see a t. So this will give us this, and a simplified version, and the final answer would be 2x square root x to the power of 6 minus 4, and we're done with this problem. So this is what the fundamental theorem of calculus is all about, and hopefully you were able to learn a thing or two about it. Now, I highly recommend looking over past exam FRQs to get more practice on this concept, as it is guaranteed to show up on the test. Thanks for watching.